All right, so we left off on part D, on the example problem yesterday. It says calculate the tension in the string when the bob is at its lowest position. Remember, we got a pendulum. We're dealing with a pendulum. At its lowest position, it is obviously, that's the equilibrium position. It will be moving. If it's released from the right side, it will be moving to the left with some speed v, which we've already calculated. And it says calculate the tension in the string when it's at its lowest position, which means we need to determine the magnitude of a force. And that force, to analyze forces, I first do a free body diagram. So I'm gonna erase my string here so it doesn't interfere with my forces. So what forces are acting?
The tension force and force of gravity. I
got a tension force, which I'll put Ft. I only need to worry about one tension now instead of two like we did yesterday. Now what can I say about the size of mg relative to the size of the tension force?
It's smaller.
It has to be smaller, right? Good.
The force is always
towards what?
to the center.
Towards the center. We're moving in a circular arc. So at the bottom of the arc, the net force must point towards the center. If it didn't, if mg was the same size as the tension force, then it would get to here, and then it would move in a straight line at constant speed. Because that would be Newton's first law. An object with no external net force, meaning the two forces would cancel out, will travel in a straight line with constant speed. So because it's moving in a circular arc, obviously it must have a net force that points towards the center of the circle. And it is accelerating, right? We learned in circular motion that any object that is actually curving is accelerating, even if it's moving at constant speed, but this one isn't. And so if we have acceleration, then we can apply Newton's second law, which says the net force equals mass times acceleration. At the bottom and the very top of a vertical circle, the net force is entirely directed towards the center of the circle. Entirely. At any other points, it's not that easy, and that's why it's not uniform circular motion. And so this we would have to be a lot more careful because we would have an acceleration that wouldn't point towards the center of the circle. So the net force would not be entirely centripetal. But we don't deal with that in this class. We just deal with when the net force does point towards the center of the circle, at least mathematically, when we have to calculate this stuff. So the net force in this case, because it is at the very bottom, is centripetal, and the acceleration is therefore centripetal. And technically these are vectors. The net force and the acceleration are vectors. So I'm just going to define, since the acceleration does point up, I'll define up as the positive direction, so my net force also must be positive. And I also know that the centripetal acceleration, the magnitude of it, is equal to the speed squared, the linear speed squared, divided by the radius r. Where in this case, the radius would just be the length of the pendulum, right? The circular arc through which the pendulum is moving has a radius equal to the length of the pendulum. All right, so the net force, I need to expand that out. I have a positive tension force because it points towards the center of the circle in the same direction as the direction of the acceleration. And then I have a negative weight force, so minus mg is going to equal mass. And I substitute v squared over the L for the length on the right side instead of the centripetal acceleration. And so to calculate the tension, I just need to add mg to both sides. So I get mv squared over the length plus mg. Not everyone brought mass to the party, so I can't just cancel out the masses, right? And so now I just plug and chug. The physics is done. At this point, it's just arithmetic. I just plug in the values and chug it out. The mass of the pendulum is 1.5. The speed, do you guys remember what the speed was?
It was
0.914 meters per second. That gets squared. Divided by the length, which was 1.25. And then to that, we must add 1.5 times 9.8. And you all should be able to do that in your head.
It's at least one.
What's that?
It's at least one.
You ever seen Rain Man?
Yes.
You know that guy, he's based on a real person?
Yes, it is.
Yeah. Great movie. Yeah, 15.7. 15.7 newtons. course, I'm an excellent driver.
Wait, so Mr. Graham. So like, when we're doing this on the AP test, will they count, or like, will they count a point for you plugging in those numbers? Like.
Sometimes for making the correct substitution, sometimes it's just for arriving at the correct numerical answer, if it's a numerical problem.
Because like sometimes I'll just like get the equation and then I'll just put it in the calculator.
Occasionally they award a point for plugging in the correct values for the correct variable, so I can't guarantee it, you know. To be on the safe side, if you're not pressed for time, you want to show as much work as you can. If I was grading it, I'd be fine with that because really the physics stops here and then it's just plugging in the calculator. If you have the time, I'd say write it out. If you're pressed for time and you're trying to get as many FRQs done as possible, then I would probably skip it and just punch it in real quick. All right, part E. Calculate the period of the resulting oscillations. All right. Well, this one's easy. We have the equation for the period of a pendulum. It's just 2 pi times the square root of L over G. That's on your formula sheet, written exactly like that. Remember, this is for small angles. So in problems, it'll usually state, you know, a pendulum swings with small angle, right? And at that, if it's a small angle oscillation like we talked about yesterday, then the release angle does not affect the period. So remember that. All right, so the rest of this I just plug in. 2 pi square root of our length, 1.25 over G, 9.8. So real easy. The simple harmonic motion part of this problem is actually pretty easy. (1.25) divided by 9.8 square root times 2 times pi. 2.24 seconds. And then part F. If the bob's mass were doubled, how would the time calculated in part E change? It wouldn't. Because the mass does not dictate the period of a pendulum. Or the period of a pendulum is independent of the mass. That's probably how I'd state it. And you've proven that at this point. Now, to wrap this up, I like talking about when I was in a lot of universities have these, a lot of museums have these. I think they're called like Foucault pendulum or something like that. But it's really large pendulum. Like the engineering department at my school, my university, it was actually hung from the second story ceiling, and then there's a big hole cut, and then it went through to the first floor, to the floor. And they would have a person that would go in every morning and put a bunch of pegs around in a circle around the pendulum. And then it was a really large one, really huge mass on a really strong rope. And they just move it to the side and let it swing. And it would swing all day long. And it's kind of interesting because the swinging pendulum does not get affected by the rotation of the Earth. And so as the Earth rotates, unless you're on the equator, it's not going to work. But anywhere other than the equator, as the Earth rotates, underneath the pendulum will actually start knocking those pegs down because the Earth rotates underneath it. It's really easy to visualize if you're like on the North Pole or the South Pole, because you got a pendulum swinging back and forth here, and the Earth turns. And so as the Earth turns, the pendulum doesn't. The pendulum keeps swinging in the same orientation, so it's going to knock the pegs down throughout the day.
There's also like those little spinning toys, right? And then like someone used that to measure like the circumference of the Earth. That's kind of the same thing. There's like the thing where like, because if it's spinning, right, it's not affected by the.
Oh yeah.
Yeah, I think you know.
I don't know if that's the same physics, but.
I think it's similar.
Is it like in something where it goes back and forth like this?
Just the circular motion.
Okay. I don't know if that applies here.
No, you were just talking about like it does apply. It's really
Okay.
I promise.
Okay. Gotcha.
Sorry.
But anyway, even if you're over here, it'll still work. It just won't work at the same rate. Because according to this, yes, the pendulum's going to move, but if I set the oscillation out and into the board here, it will maintain that same orientation even as the Earth rotates underneath it, and it will still knock down pegs throughout the day.
That's cool.
It's pretty cool. It's pretty cool. They're real big, real long periods. They take a long time to swing back and forth, and they go all day. I think they might have to lift it up once or twice throughout the day, but it's pretty cool. Sometimes you'll see a group of people watching it when it gets real close, and they'll be like waiting for it to knock down the next peg. They're like, oh, and then it just squeaks by. Because it takes a while, it gets closer and closer and closer and closer and closer. Anyway, that's it for this unit. Go ahead and work on the quest assignment for the rest of the period. I will point out the last set of problems. Let me just point out the actual numbers. Number 22 says, what will be the reading for the hours? You will get an answer in hours of something point yada yada yada. That many hours. The reading for the hour hand is just that number. So if you get a reading on the hour hand of 8.736 hours, the hour reading is just 8, right? And then you have to take that extra amount of time. In the next problem, what's the minute hand pointing at? Then you say, all right, well, the minutes are this many minutes plus some seconds. And then the next one says, what are the seconds pointing at? So if you get, in my case, it was 6 hours. But my answer is actually 6.521977 hours. That's how many hours had elapsed. But the clock, hour hand, is pointing just beyond the 6 hour mark. Right? You don't read the minutes or the seconds based on the hour hand. You just look at what hour it's telling you. Then you look at the minute hand for the number of minutes that have elapsed. And then if you're really interested in how many seconds have elapsed, then you don't look at the minute hand. You look at where the second hand is. Okay. So you should have integer answers for 22 and 23. And is it 24?
Yeah, 24.
Yeah. 24 can have a decimal, but 22 and 23, you want integer values. Round to the lower integer. All right. Everyone at home, goodbye. Unless you're going to jump on Zoom.